Hello, Allegheny College astronomy students, and welcome to another introductory astronomy class with Bella and me, Jamie Lombardi. This is the lecture for Friday, April 10th, and we'll be continuing our discussion of Chapter 16 on galaxies and the foundations of modern cosmology. I'd like to start out often with an astronomy picture of the day, so let's go ahead and do that here. I picked one from back in 2017. And this is interesting. It brings together a few different things that we've been talking about. One of them is gravitational lensing, the fact that mass can bend the paths that objects follow. In particular here, the objects I'm talking about are photons of light. And we'll learn today about quasars, and this is actually 4 images of the same quasar. There is a galaxy which is lensing that quasar. These two objects happen to be almost on the same direction of the sky. And so light from the quasar behind it is being bent around that particular lens. And we get to see 4 different images of it as a result. Some of the light had originally been going up and then was bent down towards us, the observer, some to the side and then bent toward us again, some to the other side and bent toward us. Some of the light was going down a little bit, but it was bent up towards us, and that's why we see those 4 images. And the light travel time from each of those paths of light is slightly different. And when the quasar flickers, you will see actually the timing of that flickering being a little bit different. Not only does it start at a little bit later or earlier time, depending on which image you're looking at, because of the differences in the light travel time, the time between 2 flickers is going to be stretched or compressed, depending on which one you see first. As the universe expands more, something we'll be talking about today, there's more distance for that light to travel. And so the timing between 2 consecutive peaks in a flicker is going to be stretched out a little bit. So it's actually by measuring quasars like this one here that you can measure the expansion rate of the universe. That's one way by which you can do it. So there's a galaxy here, here's a galaxy, a galaxy, a galaxy, just like the ones that we've been talking about recently. Okay, well, at the end of last class, we were discussing supernovae, white dwarf supernovae, and how they can be used as a standard candle. Remember, all white dwarf supernovae occur the same way, where a 1.4 solar mass white dwarf, which is accreting matter from a companion, blows up. And so they all have essentially the same peak luminosity. And whenever you can know the intrinsic luminosity of an object without measuring its distance, that is what's known as a standard candle. And in fact, by measuring the brightness, you can calculate then the distance to that object. So we saw this last time. I'll point out here that, look at this white dwarf supernova. It's as bright as the rest of the galaxy combined. That's how bright these things are. And that makes them very useful for being able to see the far edges of the observable universe. Now, we have a little interactive figure here that can help us to explore white dwarf supernovae's light curves in a little more detail. On the vertical axis, we have the apparent brightness, and on the horizontal axis, we have the time in days. And the way that this works is that the white dwarf supernova gets very bright, and then it dims off gradually with time. So when it's as bright as the rest of the galaxy, then that's what's called the peak brightness. And so, since all of these white dwarf supernovae occur the same way, what you can do is say, okay, well, let's say that this is the apparent brightness of a particular white dwarf supernova that was observed. It's nearly 10 to the minus 4 solar luminosities per kiloparsec squared in apparent brightness. And then it gets dimmer and dimmer and dimmer as time goes on. Now, all white dwarf supernovae, to a wonderful approximation, have the same peak luminosity of 10 to the 10 billion solar luminosities. And so at this distance of 1,000 kiloparsecs, a megaparsec, the predicted brightness would be 820 solar luminosities, much more than this. But imagine you put the object further and further away. As I drag this slider here, I still have the same intrinsic luminosity, but I am guessing different distances, and so with those different guesses for distances, I would get different predictions or guesses for the brightness. And if I go to really large distances, oh, now the predicted brightness is much less than what the peak brightness was before. Let me try to match it up as best I can. So here, I'll bring it back. Okay, so somewhere right in about here, right around 10 to the minus 4 solar luminosities per kiloparsec squared. And what I've done is I've adjusted the slider to find the distance to this object. 2.8 times 10 to the 6 kiloparsecs, or 2.8 gigaparsecs, a giga being a billion. So because all these white dwarf supernovae occur with the same intrinsic luminosity, we use them as standard candles, and we can measure distances to them up to 10 billion light years away, up to 10 gigalight years. So in summary of this chain of techniques that we've used to measure distances to objects, we start with radar, which allows us to measure things nearby in the solar system. Parallax works out to 1,000 or so light years, but remember it's 28,000 light years to the center of the galaxy. So parallax is not going to work throughout the entirety of the galaxy. To go out further, we need to use methods like main sequence fitting. And you can see here in this graph that main sequence fitting works from inside of 1,000 light years out to 1,000,000 or more light years. And so now we can actually start to reach or almost reach nearby galaxies, like the large and small Magellanic Clouds, the Andromeda Galaxy. These are on the order of 1,000,000 light years away from us. Cepheid variables really allow us to probe nearby galaxies. Cepheids are a type of variable star, remember, that oscillate, and their oscillation period is correlated with their luminosity. There are other variable stars as well, and these are the ones that Hubble, as we'll see today, used to measure the distances to nearby galaxies, including the Andromeda Galaxy. And then to measure distances to faraway galaxies, hundreds of millions or billions of light years away, we use other distance standards. We mentioned the Tully-Fisher relationship, and just today, again, the white dwarf supernovae. So Edwin Hubble solved this puzzle of the spiral nebulae. There was this great debate as to whether these nebulae that were being seen were objects that were within our own galaxy or that were external to our own galaxy. And the way Hubble settled this debate, the Shapley-Curtis debate, is by measuring the distance to the Andromeda using variable stars. And what he realized was that the distance to Andromeda put it well outside the extent of our own Milky Way galaxy. Here's an image of the 100-inch telescope, that's 100-inch in the diameter, used by Hubble at Mount Wilson in California. So the other thing that Hubble did was he took someone else's observations, and those were of redshifts of galaxies. And remember, the larger the redshift, the faster something's going to be moving away from you. And at least at slow velocities, velocities not comparable to the speed of light, the redshift percentage is equal to the percentage of the speed of light that the object is moving away. So in this particular graph, you can see up near the top here that this is what a spectrum would look like if the galaxy weren't moving with respect to us. And what you actually observe is that same pattern, but with the wavelength shifted over by 5%. And so in this example, what that means is that the galaxy is moving at 5% the speed of light away from us. As it moves away, the waves coming back towards us are stretched out because each peak of the wave has a longer distance over which it needs to travel. Here's the general formula down here. Whatever the fractional shift in wavelength is, here lambda represents wavelength, delta lambda is the change in wavelength. You multiply that fractional shift by the speed of light c to get the speed of the galaxy. So let's imagine we're doing the kind of thing that Hubble became ultimately very famous for. You pick a galaxy, M106, you measure its velocity and distance, and you put that on a diagram, and then you do that for some other galaxy, and another one, and another one. And you do this for lots of galaxies. Each dot here represents an individual galaxy. And what you find is that the velocity that the galaxy is moving away from us is correlated with the distance to that galaxy. There's, in fact, a straight line that you can fit through the data. And although there's a definite scatter around that line, the percentage or relative scatter gets smaller and smaller the farther you look away. So while nearby galaxies, like those within our local group, can really be having a mixture of velocities, in fact, Andromeda isn't even moving away from us, it's moving toward us. As you go further and further away, galaxies are without fail moving away from us, and that motion is actually described quite well by a straight line for velocity versus distance. So Hubble discovers here that the universe is expanding, and that the further away you look, the faster the object is moving. The slope of that line we're discussing is now called Hubble's constant. And remember how slopes are taken. They're rises over runs on a graph. And so in this case, the vertical axis is velocity. So a change in velocity is just the velocity because this curve goes through the origin. The galaxy that we're in is not moving with respect to us. So there's the point 0, 0 that we can fit the line right through. And so the rise is velocity, and the run is distance. Pick any point on that line, and the slope is its velocity divided by the distance. Now, often what is done is that equation is inverted. If by some means you know the distance to the object, then you can multiply by Hubble's constant and solve for then the velocity. And we see here that relationship that was mentioned. The further away something is, the faster it is moving. And also, sometimes you use this to measure the distance. And in fact, this to determine the distance. And in fact, this is probably the way that it's most often used, because you can use the Doppler effect to measure the velocity of an object, the galaxy. And once you have established Hubble's law and Hubble's constant, you take that velocity and you divide it by Hubble's constant, and you get the distance to that object, the galaxy. And so here in this particular case, all three of these equations are really the same. They have the same information content. We've just solved for each of the three variables individually. Okay, so let's think about what this implies insofar as our universe is concerned, how it behaves, and ultimately what its age is. And so in this lower left interactive diagram, we can imagine these little dots here representing galaxies, and the Milky Way is one of them. And over time, the dots are all moving away from the Milky Way. And not only are they moving away, note that the ones that are farther away move faster away. Now, in this particular playing, we have the Milky Way at the center. That's our vantage point. But here, let's look at it again with the Milky Way off-center, and you can see that really, if you imagined you were on the Milky Way, you could still see the same thing. Everything's moving away from you. But if you pick any other galaxy, maybe that one, you see the same kind of effect, that every galaxy is moving away from you, and the farther ones are moving faster. So it's not that we're special here in the Milky Way. We shouldn't be so egocentric. It doesn't matter what galaxy you're at. Any one of them will have the other galaxies moving away from it with the same kind of pattern of motion. Now, in this movie that we're playing here, notice that there has been a grid that has been superposed. And within any one of these grid cells, the galaxy just continues to exist. So it's almost like you had a floor with lots of square tiles on it. And as you stand on one of these square tiles and your friend stands on another square tile and your other friend stands somewhere else, as the tiles expand, the distances between you and your friends expands, but you remain on the same tile. Your friends remain on the same tile as well. An analogy that people often make when talking about the expansion of the universe is to consider a balloon as it expands. And you can make little marks on the balloon here, A, B, C, and D. Those represent galaxies. And as the balloon expands, the distance between any two of those marks goes up. And not only that, imagine you're living in galaxy A here. Galaxy B is moving away from you, galaxy C is, galaxy D is. But the farther away the galaxy is, the more space there is. In this case, that space is being represented by the rubber sheath of the balloon. The more rubber there is to expand, the more space you're creating between you and that other object in any given elapsed amount of time. And therefore, the faster that object would move away. Note that D moves away from us faster than galaxy B moves away from us, because of the fact that there's more space between us and D. Now, conventional wisdom is that the expansion rate of the universe is everywhere the same. That's a fundamental tenet of cosmology. And just this week, there's a paper that came out which is challenging that principle. And so I would be remiss not to mention that here. These are results from the Chandra X-ray Observatory, as well as XMM, I believe, where they have looked at clusters of galaxies in different directions of the sky. And these clusters have very hot X-ray emitting gas that permeates throughout them. There's this low density gas throughout. Even though it's low density, it's very high temperature, which is why it emits these X-rays. And the mass of the galaxy clusters themselves keeps that gas in place. Now, what's interesting is that astronomers have measured the X-ray luminosity of that gas in two different ways. One of the ways comes right from the temperature, and it is independent of the expansion of the universe. And the other way, this other technique, involves knowing what the expansion of the universe is. And the idea is that to get these two techniques to agree with one another, they have to say that the universe, as they look in one direction, has a different way of expanding than if they look in another direction. So this fundamental tenet that I was mentioning, that the universe looks the same in all directions, this is related to the isotropy of the universe, that it's the same throughout, or in the same any direction that you look. Right? It's in this, I should say isotropy is the same in any direction you look. And this is challenging that assumption, that tenet of cosmology. And so it may be that what we're teaching you here today as conventional wisdom will be challenged in the future, but it's a little bit too early to tell. We'll need to see if other observations come out in support of the most recent Chandra observations. As far as we know, our universe has no edge and no center. That is to say, there's no place within our universe that is more special than another. And we'll be talking more about how our universe expands and how you can envision this in this chapter and in coming chapters. Okay, here's a thought question for you. There'll be a few of them, a sequence of them, and I will use them to connect to how we can estimate the age of the universe based on our measurements of the expansion of the universe at the current moment. So let's say that your friend leaves your house and she later calls you by her cell phone saying that she's been driving away at 10 miles per hour directly away from you for the whole time, and she's now 10 miles away. How long has she been gone? It's not a hard question. Think about it. It's 1 hour. She's moving at 10 miles per hour. She's gone 10 miles. It must have been an hour. Now, hang on here with me. Humor me for a moment. What if she's moving 60 miles an hour directly away from you, and she's now 60 miles away instead? How long has she been gone? Again, 1 hour, right? If she's 100 miles away from you, moving at 100 miles per hour, she's been gone. You guessed it, 1 hour, right? So why am I saying this? Well, when you look out at our universe, this is what our universe is like. As you look to objects that are farther away, they are moving faster away in proportion. And so if you play the clock backwards, then you can imagine that everything was on top of the same position in space all at the same time. So take into account the previous example that we were talking about, where you had your friends moving away from you. One was 10 miles away, one was 60 miles away, one was 100 miles away. If you play the clock backwards, they would all get back to your house at the same moment. Even though they were at different distances from you, their velocities were different, and if you play the clock backwards, they all left at the same time 1 hour ago. And you can do the same things with galaxies in our universe. If a galaxy is twice as far away, it's moving twice as fast. So if you take those two galaxies and you play the clock backwards, they were both here at the same location at the same time. This doesn't prove that there was a Big Bang. We'll give the evidence for a Big Bang later, but this is the first hint that there was a Big Bang that began our universe. That if you play the clock backwards, it seems to be that everything came from around the same place at the same time. Now, in the example I gave you where cars were driving away, and right now where I'm thinking about galaxies expanding, I'm keeping it simple, where the speed is remaining constant over time. We'll explore in more careful detail the fact that as the universe expands, its expansion rate is changing. But let's stick with that simple model, which teaches us a lot, where if we measure the speed now, we can pretend that it's always had that speed. And if you want to use that, then you can just pick any galaxy out there, or take several of them in average, and take the distance to that galaxy, divide it by the rate at which it's moving away from you. Distance divided by speed would give you time, the time that it would take the galaxy to have gotten from you to where it is now. In other words, if you play the clock backwards, that's the amount of time that that galaxy has been receding away from us. And so that is the age of the universe. If you measure Hubble's constant and then take the reciprocal of it, the inverse, 1 over h naught, that gives you an estimate of the age of the universe. That estimate turns out to be on the order of about 10 to 20 billion years. The accepted age of the universe is 13.8 billion years. All right, let's move on. We'll now talk about galaxy evolution. Galaxies are different from one another. We saw that there are spirals and ellipticals, for example. And there are a few reasons, starting with these two, that galaxies differ from one another. The first one is the density from which the galaxy forms. You can think of a galaxy forming from a giant protogalactic cloud that collapses down to form the galaxies within it. And if you have a particularly dense cloud, then it'll form stars quickly before the galaxy really has time to settle and flatten down into a disk. And so more dense clouds are more likely to make elliptical type galaxies. The spin of the cloud is also very relevant. The faster it's spinning, the more flattening that you're going to get, and therefore the more likely it is that you're going to make a spiral type galaxy. So depending on the density, less dense clouds will make spirals, faster spinning clouds will make spirals. So depending on the density and the spin, you might get these two different types of galaxies. Let's take a look at some movies here. We'll press play on both of them. The protogalactic cloud on the left has less angular momentum. The one on the right has more. Notice that the additional spin allows it to flatten out more easily. You're more likely to make a spiral. Whereas over here, without that random or that angular momentum, you don't have as much flattening. You're more likely to make an elliptical. And in the case of density, the protogalactic cloud on the left is high density, so stars form quickly before the galaxy has a chance to flatten out into a disk. Here, the lower density, it takes longer, and so the stars are formed later, and the disk is able to develop. Now, besides just the spin and the density, another thing that we need to take into account is the effect of collisions. Collisions occurred much more often as you look back farther and farther in time. And so that's not surprising, because the farther back in time you look, the smaller the universe was, the closer packed things were together to one another, and more likely they're going to be colliding. And indeed, as you look back farther and farther, and therefore back further and further into the evolution of the universe, you see a lot more irregular galaxies, ones that are being formed through galaxies colliding. The collisions can tend to make not only irregular galaxies, but after they've settled down, elliptical galaxies as well. Here are some colliding galaxies. Over on the left, we're zoomed out. Over here, we see the footprint of the Hubble Space Telescope CCD camera, and that is what's shown here over on the right. You see these long tidal tails, and then here, zoomed in, where the two central regions of the galaxies are colliding, we see these white bluish stars. That's because gas clouds from those two galaxies have collided and triggered star formation. The last section in Chapter 16 is on active galactic nuclei, or AGN. These are very energetic galaxies, where the energy source, as we'll discuss, comes right from the center of the galaxy. The luminosity that we're talking about here can be enormous. In the extreme cases, it can be more than 1 trillion solar luminosities. And if you zoom in on some of these regions, like this is M87. Remember, that's the galaxy we looked at with the help of the Event Horizon Telescope not long ago. The first ever black hole imaged by the Event Horizon Telescope, at least publicly released data from it. And so here we have the ability to zoom in on M87, and there's the active nucleus we're talking about. There's a jet of particles coming out from it. If we zoom in closer, remember, there's that gas cloud. We had talked about that before in the context of measuring the speed that that gas cloud orbits at, and thereby being able to determine that there's a black hole at the center that's billions of solar masses. And that's going to be a clue here. All of these active galactic nuclei we'll discover are being powered by supermassive black holes. Quasars are the most luminous example of active galactic nuclei. Here's an image from, looks to be the mid-1990s, from Hubble Space Telescope, that's showing a quasar and its host galaxy around it. Before then, before Hubble started imaging these, there was a debate as to whether quasars were within our galaxy or outside. The reason to think that they are outside our galaxy was that their wavelengths, the light coming from it, was highly redshifted. Right here are some lines from hydrogen. For example, this is what those lines would look like in a lab spectrum. HD is around roughly 400 nanometers. And now when you observe it in this quasar, it's out at almost 500 nanometers. So we're talking about, if you believe this redshift, something moving at 20% the speed of light. If it's moving at 20% the speed of light, then Hubble's law tells us that it's far away. But if it's far away, how can it be so bright in the sky? And so there was an argument, really, up through the early and mid-1990s until you started imaging and seeing that these quasars were in galaxies. The argument was, do we really think that these things are as far away as Hubble's law implies that they are? Or is there some other phenomenon that we haven't discovered yet that could explain this great redshift? Here's a thought question for you. What can you conclude from the fact that quasars have large redshifts? They are generally very distant. They were more common early in time. Galaxy collisions might turn them on, or nearby galaxies might hold dead quasars. Pause it if you like. And the answer is that you got it right. I know you got it right because all of these responses are right. And so any one that you picked would have been right. In fact, the others are as well. It turns out that there is no other phenomenon for describing these large redshifts. The redshifts are large because truly these are very distant objects moving very fast away from us in accord with Hubble's law. And if you are seeing them at great distances, remember, the further away you look in space, the further back in time you're looking. And so something that's very far away, the light from it left a long time ago, back when the universe was very young. And so B is also true here, that these objects are more common in early time. We see them at large distances. At early times in the universe's history, galaxies collided a lot. And so, yeah, maybe quasars have something to do with galaxy collisions. At least triggering those reactions may have to do with galaxies colliding. And if there were a lot of these quasars at large distances from times long ago, well, what about nearby? We don't see the quasars, but maybe there are dead quasars, so to speak, in these nearby galaxies. The nearby ones are ones that we've imaged from more recently in the universe's history. And therefore, they used to probably have be quasars, you know, or be powered in the same way that quasars were, but now they're no longer, and now they have these dead quasars within them. Now there's a line in your textbook that says, imagine that you are a master of the universe, and you want to signal one of your fellow masters 1 billion light years away. What would you use? You'd use something like a quasar because you'd need a beacon that was very bright. The answer to today's reading quiz is, I'm a master of the universe. So you write, I'm a master of the universe. I'm not saying I'm a master of the universe. You're the master of the universe. But you write, I'm a master of the universe. Hope you get it. We can tell that the size of this object that's making this bright light has to be small. The reason we know that is because its brightness varies on a time scale of tens of hours or less. And so that puts it at sizes that are comparable to our solar system or smaller. Why do I say that? Okay, imagine that you're one of these masters of the universe and you want to communicate with another one across the universe. If you have a really, really big light source, let's say it's a light year across, and you use your powers to turn down the brightness instantaneously on your light source. Well, what is the other master of the universe going to see? Well, the light coming from the front side and the back side had been shining towards your fellow master. You shut it off, and then my hands here are representing the last twinkles of light from the front and back side of the light source that you're using, your beacon. And so the front side will reach the other master of the universe and then shut off. But then the back side, which was a light year further away, will continue to shine for an additional year. So the other master does not see the light source turn off instantaneously. She sees it turn off over a 1-year time period because in the example I gave, the beacon was 1 light year across. And so the only way to get something in astronomy to flicker on and off quickly is if it is small. Imagine the object had only been a half a light year, maybe a light month, maybe a light day, let's say a light hour across. Then if you turn it off quickly, the other master will see it turn off within an hour time period. Now, the variability in observed quasars is short enough that we know the object is very small in size on the scale of the solar system or smaller. Another interesting fact about quasars is that not only are they highly variable, they're emitting light from across the electromagnetic spectrum. Here we see that it's emitting gamma rays and X-rays, which tells us that there must be some very hot gas there, but also in the ultraviolet and the infrared and even in the radio. And so there's a range of temperatures. There's a lot going on here in and around quasars. Just this week, the Event Horizon Telescope released new results. Now, I know this says 2017 here, but remember the interferometry technique that's used by Event Horizon Telescope requires that you have telescopes from across the globe sharing information with one another. And there are inordinate amounts of data that need to be shared and compiled and brought together. And these data were just released here within the last week. And this is of a quasar. And what do we see here? Here we're zoomed out the most, and we see some jet of material coming out. Here we zoom in just to this portion, and then we zoom in a little bit more. And notice that there's this jet of material coming out. Let's go ahead. I picked out a YouTube video, which I'll show you here, which will allow us to explore those data a little bit more carefully. The date is listed down in the lower left, April 16th, 2017. And now watch that date, April 1st. We're zooming in on that central region. April 5th, we've got a more close-up look. Notice this jet of material coming down towards the bottom and a little bit off to the right. And notice that the date's ticking away, April 10th, April 11th. This is dynamically changing. On a time scale of days, we see this image becoming different. When we stack them side by side next to one another, you'll be able to see that more easily. There's April 5th, April 6th, April 10th, April 11th. And by monitoring the changes in the positions of the central brightness here, you have this material that's being shot out, and you can determine that it's being moving at speeds faster than 99.5% the speed of light. So these jets of highly energetic material are being shot out, and we're seeing that through observations. Most of the time in astronomy, when you're observing things, if you take a picture one day and then you take a picture 5 days later, that object looks essentially the same. I know there are exceptions, but especially when you're looking to other galaxies, the object, if I take a picture of the Whirlpool galaxy now, and again 5 days later, I'm not going to be able to tell the difference between the two. Here we see that quasar evolving. Now, radial galaxies are a type of active galaxy. However, they are having their central engine's view blocked by dust that encircles it. And so what we end up seeing is not right down very easily to the very center, but what we do see is these jets of material shooting off, and then they're called radial galaxies because charged particles will circulate around the magnetic field lines associated with these jets, and those circulations are moving or accelerating charged particles at frequencies in the radio. And so here are some hot spots at the end of this particular radio galaxy. Here's another radio galaxy. Our view of the center is largely obscured by dust, but the lobes shoot out beyond that. Notice that this is 100,000 light years across. So these are gigantic lobes that we're talking about. Remember, the Milky Way galaxy is about 100,000 light years in diameter. So these lobes are as big as or bigger than galaxies themselves. And this is an artist's rendition of what I was mentioning about how these dusty gas clouds are obscuring our view. These radio galaxies might be called quasars if they had been oriented at a different direction and that dust was not obscuring our view. So let's talk more about how accretion of gas onto supermassive black holes can explain these very energetic quasars and more generally active galactic nuclei. what you have is material that can fall down onto a black hole, creating an accretion disk, and then material is favorably shot up along these jets perpendicular to that accretion disk. As objects fall towards a black hole, they release a large amount of gravitational potential energy. That could be converted into kinetic energy as they fall faster and faster, and then into heat as it hits upon an accretion disk. Right? That hot accretion disk is going to glow, and that's why we see accretion disks in the gamma ray and in the X-ray. Now, as matter falls down onto a black hole, you lose an amount of energy and gravitational potential energy, which is equivalent to, or on the order of, the rest mass energy, mc squared. So that's a lot of energy available. And the estimates are that you could release as much as 10 to 40% of that energy in the form of radiation. That's how you make these things so bright. It's by releasing the gravitational potential energy of the infalling mass and allowing it to escape as light. That is the energy source. So these jets that we're talking about, they're thought to originate from twisting magnetic fields that come from the inner part of the accretion disk. And then these twisted magnetic field lines will funnel the material that's being shot out. And it's around those magnetic field lines that the plasma in these jets cycle, and hence the radio waves would be emitted. So depending on where you're looking, you're going to see preferentially different amounts of different wavelengths of radiation. Close on into the black hole where it's very hot, gamma rays and X-rays. Out in the jets, you'll see a lot of radio sources. If you just look at the object as a whole, you'll get a whole range of wavelengths being emitted from it. Now, black holes exist, as far as we can tell, in essentially all galaxies. Perhaps all of them have supermassive black holes. At this point, there have been so many different supermassive black holes that have been discovered at centers of galaxies. And supermassive black holes are typically on the order of millions or billions of solar masses. Hey, be good. These black holes are essentially dormant quasars, or dormant active galactic nuclei. Like, take the Milky Way galaxy's black hole, Sagittarius A star. It's no longer actively accreting, besides the occasional snack, gas from its surroundings. And so for the most part, it's inactive at this point. It's a dead quasar, so to speak. Here's a diagram that allows us to see a correlation between the mass of the black hole, which is being plotted on the vertical axis, and the mass of the central bulge. And this implies that there is a connection between the two, which perhaps is not surprising, that the development of these black holes in galactic centers is tied to how galaxies evolved. And so as you get to larger bulges, you get to larger and larger black holes in the center of the galaxy. What do you think about that, Bella? So if you look here, as you get the curve going up higher and higher to the right, you get to more massive black holes and more massive bulges. That's not surprising, because if you've got more mass in the bulge, you have more material from which the black holes could form. And astronomers, astrophysicists are working actively to model how you build up these supermassive black holes. Well, I wanted to finish today by saying a little bit about the night sky and introducing you to the new constellations that you'll be responsible for knowing on the final exam. And there's this program, Stellarium, that I'm going to use to help show this to you. Right now, we're here on Earth in a field in good old Meadville, Pennsylvania. And we can look around in the sky. This is representing the current time of the day, and we see the sun's up in the sky. I can, if I like, jump forward a bit, hour by hour, and watch the sun go across the sky down towards the western horizon. And there it's about to set, And then once it's set, we go through twilight. And Venus is going to be the first thing that you see in the night sky, right? As the night goes by, it'll get closer and closer to the horizon, but it'll be almost directly west this week. And as the month goes on, it'll be moving closer and closer to the horizon and more towards the north. But you can see a few days ago, Venus actually passed by the Pleiades star cluster to within 1/4 of a degree of it. Remember, the moon is a 1/2 of a degree wide. So look for the Venus, the planet Venus, off to the west. If you get out binoculars, you can zoom in on it. And you may even be able then to notice that it is elongated. You won't be able to see it quite so nicely as this. I'll go ahead and pause time so that it doesn't drift off the field of view. With binoculars, you won't be able to see this level of detail, of course. But you can appreciate why it will look elongated, and that's because it goes through phases. Remember, that's what Galileo Galilei discovered 400 years ago. Like the moon, Venus goes through phases, and it makes sense that the bottom portion of Venus is illuminated here because remember, the sun has just set down to the west, and Venus is not emitting its own light, but rather the sun's down here below the horizon. It's shining on the bottom part of Venus, if you will, which is then coming back towards us. So you'll be able to see Venus in the Taurus the Bull constellation. There's Pleiades. There's the Eye of the Bull, Aldebaran, in the Hyades star cluster. You'll still be able to see, even though we're now into spring, those constellations of the winter hexagon that we learned about, including Orion the Hunter, the Big Dog, and others. But what I want to do is start to turn my attention more towards the top, where we see Leo the Lion, punctuated by Regulus, and the tail end of the lion back here in the triangle, there's Nebulae, the tail of the lion. And at this point, I would like to show you how you can, arc to Arcturus. There's the Big Dipper. These two pointer stars would point up and to the left here towards the North Star. And you can follow the arc of the handle to arc down to Arcturus. And so let's start to allow a little more time to go by this evening, and we'll see what else comes up over the horizon. Vega, that is going to be one of the stars here that I'm about to teach you. I'll go all the way until the wee hours of the morning, right before the sun rises. We'll back it up here a little bit. And so this is around 5:30 in the morning. And this is going to be looking towards the southeast at this point. You can look for the planets Jupiter and Saturn and Mars. And if you look up high in the sky, we'll see the summer triangle. Now, I said that this was 5:20 in the morning, but if you wait a month, you'll be able to see this an hour earlier. So in May, you would, or 2 hours earlier, you would see this at 3:20 in the morning. Or in June, you would see this at 1:20 in the morning. Or in July, you would see this at 11:20 at night. And so you'll see the same sky, essentially, at different times of the night because the Earth has progressed on its orbit around the Earth. You can start to appreciate why this is called the summer triangle because I've moved this ahead to July now, and you'll see over the eastern horizon that summer triangle. There's Vega. That's going to be in the Lyra the Heart constellation. You look for this triangle and this little squished rectangle right there. Here's Altair, and Altair is in Aquila the Eagle. So you look for this egg-shaped pattern of stars with some other stars coming off to the side representing the wings and tail feathers of the eagle. And here you have Deneb. I'll zoom in a little bit on it so you can see it a bit better. And Deneb is part of the Cygnus the Swan constellation, also known as the Northern Cross. So here I have it sideways, but this would be like the vertical bar of a cross. This would be the horizontal bar. Or if you think about this as a swan, Deneb is the tail of the swan. Alberio over here, that is the head of the swan. And I'm going to ask you to learn Deneb. And now there's the body of the swan with its wings off to the side. So there are some things that you can look for in the coming weeks and months in the night sky. We'll be learning and concentrating on, for the final exam, all of the constellations, but these will definitely be asked of you, those from the summer triangle. So know Deneb and Vega and Altair, and know the constellations that they're within. If I go back to the PowerPoint presentation, we can review. Here is the Lyra the Harp constellation, and this bright star in Lyra the Harp is known as Vega. The Ring Nebula, by the way, is a planetary nebula between the two stars at the base here of this twisted rectangle. There's Vega. This corner of the triangle is shared by this corner of the parallelogram, or the bent rectangle. Here's Cygnus the Swan, or the Northern Cross. The star I want you to learn there is Deneb, the tail of the swan. And notice in this image there are lots of stars in this vicinity. That's because Cygnus is flying right along the Milky Way galaxy. And so if you get to a dark enough patch and you find Cygnus, that might help you to identify the Milky Way. Or if you found the Milky Way, you might be able to use that to help you find Cygnus. Here's Aquila the Eagle. And the bright star in Aquila the Eagle is, do you remember what it is? This one right here? That's Altair in Aquila the Eagle. So that's all we have time for today. I hope that you are doing well. Stay safe and take care. Bye-bye.